So today we'll discuss the conditional probability. So this class should follow the one about the distribution of exit point that I will remind now. So let me remind you what we have seen in the previous class about the probability of exit from a domain. So if this is a domain omega and we have a process x of t, this is a stochastic process, a solution of the stochastic equation x dot equals b of x plus sigma w dot, where omega is the Brownian noise and b of x is a deterministic vector field. So what we have discussed in the previous class is that we can give an equation, a partial differential equation, for the probability that the process starting at position x will hit the part A before it hit the part B. Right? So if we call tau of A, this is the first time t, let's call tau, that the infimum of t such that x of t will hit the boundary d omega, which I call d omega A. So this is t positive. And if we have tau b the first time the process will hit part B, then what we have calculated in the previous class is that the probability that tau A is less than tau B when the process, condition that the process started at position x at time 0, which means x of 0 equals x. Then we found for p of x an equation which, let me remind you, when b was equal to 0, we found that, and sigma is identity, sigma equals identity, then we found that p satisfies Laplacian p equal 0 on omega, p equals 0 on the omega b, p equals 1 on omega A, and everywhere else where we assume that the particle is going to be reflected, we have, for example, dpdn, the Neumann derivative, equals 0 on d omega minus d omega A and d omega B. Right. So now what we'll be interested in is to actually build a process and find the associated stochastic equation for a process that will only escape in A and never in B. So for this, we would like to start with the probability distribution of such a process. Let's call probability star of the process to be located at point y, condition that it started at point x at time t. So this is the probability that x of t belongs to a volume element of y plus dvy, condition that the exit time is occur in A before B, when the particle initially starts at x. So TA and tau b has been defined in the previous slide, and now what we would like to calculate is to estimate this probability in terms of the probability distribution function of the process x of t, where we assume again that x of t is solution of x dot equal b of x plus sigma w dot. So for this, let me remind you what Bayes' law is telling us is this is the probability that x of t is between y and in the volume located around y, and tau a is less than tau b, and x of 0 equals x. So this has to be divided by the probability that tau a is less than tau b. Actually, this is condition that x of 0 equals x, and this is x0 equals x. Alright, so this is precisely what Bayes' law is telling us. Now, it becomes interesting to understand now what is the probability of the numerator. The probability of the numerator becomes precisely the probability that x of t is at y plus dvy, and now this event is independent that tau a is less than tau b, so this is just now condition of x0 equals x. And since this is independent, now we have to multiply by the product probability, and so now this is we have to use the Markov effect, the Markov property, that if at position y, which is in the future, t, the x of t is located at y at time t, we don't care that it started at x at point 0 because it's a Markovian process. So then what is important is the last event. So we can rewrite this as tau a less than tau b, and x, which now we can use a change of time, x of 0 equals y, because we assume that this event is the same as the one that that started at position 1, and again this is correct because we have a Markovian process. And now we can divide by what is the denominator, which is tau a less than tau b, condition of x0 equals x. Now this can be rewritten as the probability transition function for the initial stochastic equation to find the particle at y when it started at position x. And now we simply have p of y, or let's call it q of y, divided by q of x, where q by definition, q of x, is the conditional probability that the process escape in A before B when the initial position is equal to x. So this formula now is important because it will allow us to have a better characterization of the conditional process. So let's call the conditional process x star. So x star is solution of a stochastic equation, and now we would like to, which is b star of x plus sigma star w dot. And now we would like to characterize these new elements, which are the drift. So how to calculate the drift b star and the diffusion tensor in terms of the element of the stochastic equation for x, which is b, and sigma of x, and the information coming from the probability, the transition probability function. So for this, we are going to use the Ito calculus. So let's write the, let me remind you the classical formula for the expectation of the differential quotient, which is xt plus delta t minus xt, which is for a general process can be written as t plus delta t, which is b of x ds plus integration from t and t plus delta t of sigma x of s d omega s. And now we have seen this formula early on, that the limit of the expectation of x of t plus delta t minus x of t divided by delta t, condition that x of t equals x, and the limit as delta t goes to 0, we simply have to take the limit in this formula. So we have already shown that this was b of x. So which means that b of x, we can now use the expression with the probability distribution function, which is the expectation of x of t plus delta t minus x of t, condition of x of t equals x. So this is simply y, probability to jump from x to y during the time step delta t, minus the so we can now use the fact that at x the fact that xt equals x, so this can be written p of delta t, making a transition from x to y dy. And so this can be written y minus x, probability, transition probability from x to y, and we have to integrate over all y. Now using, and this is by definition equals to b of x delta t plus a term that is negligible in delta t. So now if we use the conditional the conditional probability for the process star, and let's write, so for the process x star of t, so we are now going to replace in this expression p by p star. So by definition, b star of x delta t equals the integral from x y p star of delta t y x dy. And now if we replace this by the expression for p star, this is simply y minus x p delta t of y conditioned on x multiply by py or qy divided by q of x, and this is dy. Now q of y divided by q of x can be written using a Taylor expansion as 1 plus y minus x q prime of x divided by q of x plus y minus x square. This is the remainder term. Okay, so now if we replace this in this equation, we'll get the first term will give us y minus x p delta t. This is the conditional probability for the initial process, plus y minus x square q prime of x, q of x, multiplied by the probability distribution p delta t, y of x, and we have to integrate everything dy. So now, by definition, this is equal to the initial drift. So this is exactly b of x delta t. So this is coming from this part here. And the second term here is exactly the characterization as we have seen before, of the variance, which can be written. Now we integrate with respect to dy, so x is fixed, so this is q prime divided by q. And now if the tensor for this term is sigma, so we get precisely here sigma square of x. So we have found here that b star delta t is equal to b of x delta t, and so here we have forgotten to write multiplied by delta t. So is equal to the sum of the two terms. So finally we get b star of x equals b of x plus q prime of x divided by q of x sigma of x. Which is the characterization of the drift of the conditional process with respect to the drift of the initial process, and the conditional probability q, which account for the information about the geometry of the domain and the location of A versus B. Now we can do the same for the characterization of the tensor. So by definition, let me remind you that the formula, we have the identical formula for the variance. So the formula is that, so again, I write everything in dimension 1, and I will give the general formula in higher dimension after we are done with this. So it's the difference x of t plus delta t minus x of t square, everything divided by delta t, and condition that x of t equals x. So the limit of this as delta t goes to 0 equals, by definition, this is sigma square of x, which is the tensor of the initial process. And now using the same characterization, we can write that sigma square of x delta t. So this is exactly the same procedure as the one written in the previous slide, can be written as y minus x square multiplied by the probability density function to jump from x to point y during time delta t, and we have to integrate over all dy. And this is here plus a term that is negligible to first order in delta t. So now, if we would like to use this formula, we can characterize the tensor for the conditional process, so sigma star square of x delta t equals, this is the integration over the domain omega of y minus x square. And now we have to use here the conditional probability distribution function for the process. So this is p star, which can be written p delta t, y condition on x, q of y divided by q of x dy. And so now I will leave this for the for anybody who is interested. Now using the same argument of a Taylor expansion of q of y near x. So we need to do a Taylor expansion as we did before. And replacing here in this formula, we get precisely that this is the first order, that the ratio, as we have seen, q of y divided q of x start with 1 plus. And thus, this will give precisely the diffusion tensor sigma square of x delta t plus terms that are negligible. And so what we have found in here is that sigma square of x is equal to sigma of x. So the tensor is not affected, they are not changed. The tensor is the same for both the conditional and the non-conditional process. Okay, so this is now let me say one word about the higher dimension. So this is dimension 1 we have seen in here. In higher dimension, the formula is very similar, so I will leave this to the reader. So in dimension in dimension k, the drift b star for let's write the k component, or look, the q component of x is equal to the q component for the non-conditional process plus sigma sigma transpose applied to dq q. So this is the vector, and then we need to have the q component of this. So this is the matrix apply to this vector, right? So we can always write this sigma sigma transpose. So this is ij, and we have to sum, let's sum it I q q, and we need here, q is not great here, let's call it little p. For this is p, and so I, and we need here p, and we have to sum here. So this is I, we have to sum here over I. So this is the meaning of this term. And in dimension k, since the tensor are equal, it has to be equal in terms of tensors. So sigma kq of x equals sigma star of kq of at position x at any point here of the domain. Okay, so now what I would like to make a remark is that by definition, this process is not necessarily easy to manipulate for simulations. So indeed, because at the part of the boundary where the process is should not hit this part, q of x equal to 0 for x which belongs to the part B, where the process should not hit this part, because it should exit in part A before hitting this part B, which means that in simulations this leads to an infinite drift here. So this is the drift here tends to infinity as the distance from x to the boundary d omega b tends to 0. And so this can lead to a drastic effect on simulations. So in general, to do a simulation with a conditional process, it's better actually to simulate trajectory for the process that is not conditioned and select the trajectory that will hit A before B. So we have two types of trajectories. A trajectory that start in X and that are going to hit B, and the trajectory that start in X and are going to escape in A. And thus, if we are interested in statistics, for example in mean first passage time statistic, then it's more relevant for the calculation to just select the set of trajectories. So the trajectories which we can call the ensemble of X of S, such that we're sure that the exit, where the exit time, they are all exit in A. So this creates an ensemble, a sub-ensemble of trajectories from which we can calculate, for example, the exit, the mean conditional exit time. Let's call it tau conditional. And so now let's write an equation actually for this conditional escape time. So now we are going to discuss here the conditional mean escape time. So this is the time when the process starts at position X and escape in the part of the domain A without touching B, and assuming the rest of the domain here, the particle is reflected. So this is a reflective part. So to calculate the mean first passage time of the process, we have seen that if we have a process X star which is satisfy the following equation: B star of X star plus sigma star of X star d omega, then the mean first passage time of the process is solution of the equation. That, so let's assume here that sigma star equals the identity, or let's say square root of 2d, the identity. So we have here d Laplacian of W plus B star gradient W equals to -1, and by definition we need to have the omega equals to 0 on A. So this is the condition, and so we need also reflecting boundary condition. So let's write d omega dn plus B star dot n W equals 0 on the reflecting part, which is d omega minus d omega A minus d omega B. And on B, we need to have that the total, the time should be finite. It should not be infinite. This is the condition that this is the so this is on B. And so now suppose we can write this in terms of the drift of the initial process, which is B star equals B plus so here we have sigma sigma transpose, which is simply 2D multiplied by identity and this is the identity, applied to gradient P divided by P, or gradient Q divided by Q, where Q was the conditional process. So which means that we have the equations d Laplacian W plus B gradient W plus 2D gradient Q divided by Q multiplied by gradient W equals -1. And now if we assume here for simplicity that B equals 0, then we are left with an equation which can be written as d Laplacian W multiplied by Q equals -Q. Just multiply everything here by Q and use the fact that Laplacian Q equals 0. So this is the solution, the reduced Laplacian equation for the mean first passage time of the conditional process, where WQ by definition should be equal to 0 on B because W is finite and Q is 0, and WQ is also equal to 0 on A, simply because Q is 0 and W is 0. And we have also the boundary, the reflecting boundary condition, which can be calculated on the reflecting part. This is simply derivative of W multiplied by Q divided by dN, which is W dQ dN, plus Q dW dN, which is 0 because this is a sum of two terms which are 0. Okay, now let me give you some applications for these conditional processes. So the first application came from the following problem. This is the time to escape from a domain where we have an annulus here. So a particle is reflected here in this boundary, can either hit the region, let's call it A, or can escape here through a region B. So we are interested in calculating what is the mean first passage time to B. That is the mean time to hit B, to escape in B, before hitting the region where you can see here the domain A. So if A is a radius, A is simply a domain of radius R less equal to A, the entire domain omega is R less than, let's call this capital R. And the region, so and this is only a small fraction, so B is a small fraction characterized, let's say, by the angle of opening, which is epsilon. So B is simply characterized as for R equals capital R, and let's say the angle theta is less than epsilon. So how to calculate the conditional mean first passage time for the process that will escape in B without never touching A. So this is the first question, when, for example, the ratio A divided by capital R is small. So how to calculate this? So this was calculated in the article with Adi Taflia in Journal of Chemical Physics, and I think this was in 2007. Now, the case where A divided by R is of the order 1, of course it's less than 1, that is, suppose this is a very narrow region and we're interested in the mean first passage time for the trajectories that can be reflected here but never hit A, and they have to escape in B. So this I will leave these two questions unresolved here. So the first one, the solution for the probability and the mean first passage time can be found in this article. So this is Adi Taflia and myself. And the second question, I think we have left it open. So any calculation will be of interest. So we have discussed today this way of calculating the stochastic equation for a conditional process, and so this partial differential equation can be used in this specific example using here the narrow escape approach to give this estimate of this mean first passage time as a function of epsilon. And in general, this has many applications. So why this example is important? Well, this was important in the context of synaptic plasticity, synaptic transmission, to estimate the residence time of a Brownian receptor in the postsynaptic density. So this is a synapse, and this is the postsynaptic density PSD, and we were interested in estimating the time it takes for the receptor to escape, assuming that the structure can be homogenized with this following figure. So I will stop here this conditional process lecture and just give some references. Sam Carling and Taylor, in this first course on stochastic processes, 1975, they have few pages on this derivation, and also in this second courses. The higher dimension can be found in the book of Schuss 2009. And we have also a specific chapter in the new book of 2005, Stochastic Narrow Escape in Molecular and Cellular Biology Analysis and Application, where I'm giving in this book the entire calculation for the case of the annulus and the escape through a small hole.